Let me start by saying thanks very much to the organizers for the invitation. It's a real delight to be back in Santa Barbara. So today I'm going to tell you about this project, which is the result of an extremely fun and rewarding collaboration with my outstanding colleagues, Lawrence Eberhard at Amsterdam, Beatrix Moolman at McGill, and Victor Rodriguez at Princeton. And I want to emphasize that this is work in progress, so while I'll present some results, some aspects of the conceptual picture are still crystallizing, so I'm looking forward to whatever feedback people may have. So let's get right into it. I think it's fair to say that a recurring theme of this program has been the absence or dearth of a precise controllable model of de Sitter quantum gravity. And I'm not going to fix that in this talk, but it looms over the talk, let's say. Now, in Victor's talk, we heard about a very precise duality between a 2D string theory based on Liouville CFT and time-like Liouville CFT on the worldsheet. So between that 2D string theory and a double-scaled matrix integral. And what Victor showed us was that JT gravity with negative cosmological constant emerged as a sort of semi-classical limit of the worldsheet theory. Now, I think there are many interesting and exciting relatives of this theory to explore. And for the rest of the talk today, I'll tell you about one such relative of this theory that turns out to be related to a theory of 2D dilaton gravity that admits solutions with both signs of the cosmological constant. Okay, so in particular, I'll describe a new family of 2D critical string theories and argue that this family is dual to a two-matrix integral, which is characterized by a spectral curve with infinitely many branch points. And I think it's in some sense the most natural cousin of this Virasoro minimal string, or VMS, that Victor told you about earlier this morning. So the basic upshot is the following. Internally, we've been referring to this as the Liouville squared string, but please don't get too used to this name. The title is also very much work in progress. So it involves coupling two copies of Liouville CFT to each other on the worldsheet, ordinary space-like Liouville CFT. And we'll be particularly interested in this situation where the two Liouville CFTs are in some sense complex conjugates of each other. In particular, where the central charges have real part equal to 13. And in the language of Victor's talk from earlier this morning, this corresponds to the B parameter having a funny pi/4 phase. And I'll try to argue that this string theory is dual to a two-matrix integral characterized by this spectral curve. And unlike the observables in the theory Victor told you about this morning, we'll see that the string amplitudes, which we'll call A instead of V, will exhibit a rich analytic structure, including infinitely many poles and branch cuts viewed as functions of the momenta. Now let's just contrast that with what Victor told us about this morning. So this involves coupling Liouville CFT to time-like Liouville on the worldsheet, where the central charge of the ordinary Liouville was bigger than 25. And he argued that this was dual to a double-scaled one-matrix integral with this spectral curve, where this sine formula is essentially the Carty formula for the experts in the audience. And what Victor showed is that some miracle, some underlying integrability of this theory made it so that these string amplitudes, which we referred to as quantum volumes, were simply polynomials in the external momenta, pi squared, of finite degree. Okay, so that's the roadmap. So I'll start by discussing the worldsheet theory and its relation to a particular theory of 2D dilaton gravity. I will then move on to discuss some observables in the theory. And so I'll start by discussing the sphere 3-point amplitude, which is in some sense the simplest observable in the theory. And then I'll move on to discuss something more complicated, the sphere 4-point amplitude, and I'll use it as a sort of working example to illustrate the general constraints on the string amplitudes in this theory. And despite the fact, as Victor emphasized, that direct numerical computation of these quantities is difficult, we know a lot about Liouville CFT, and we'll be able to leverage that into some strong constraints on these string amplitudes. And I'll conclude by giving you a first glimpse of the dual matrix model. So let's get right into it. So now I'm a bootstrapper, so talking about the Lagrangian formulation of Liouville CFT makes me feel a bit queasy, but let's do it nevertheless. It turns out to be instructive. So we consider two copies of the Liouville action that Victor wrote down in the talk earlier, except now we consider B, we allow B to have this funny pi/4 phase, and for reasons that will become clear shortly, we'll consider the situation where this Liouville cosmological constant is pure imaginary. So we have a Liouville action for phi and phi bar, which we'll think of as complex conjugates. Now, this is fine, but it will be particularly interesting to consider a field redefinition, which rewrites these two scalar fields, phi and phi bar, in terms of two other scalars, rho, which will play the role of a scale factor of another auxiliary metric g, and capital phi, which is some other scalar field. And at least at the level of the classical action, this field redefinition maps the theory to a theory of 2D dilaton gravity with a sign potential for the dilaton. And this, a theory like this has shown up recently in a couple of papers by, a couple of very interesting papers by these folks. And the action is very similar to the cinch dilaton gravity that Victor wrote down this morning, except now the potential for the dilaton is a sign. And I write pi I b squared because in the situation that b has this funny phase, then b squared is pure imaginary. So the argument of the sign is real. Now, the equations of motion for this theory are the standard ones in dilaton gravity with a potential. And what's interesting is that this theory has infinitely many classical solutions and corresponding to zeros of this potential. And what you notice is that the classical solutions of the theory alternate between positive and negative curvature on shell due to this relation. And so this will at least provide us with some heuristic motivation to take more seriously the worldsheet string theory that we get when we couple the two Liouville CFTs, but from the more axiomatic bootstrap approach. So are there any questions about this before I move on? Okay, good. Okay, so let's get into the string theory then. We define the worldsheet theory as before by the following non-perturbative CFT. So we couple Liouville CFT with central charge C plus equals 13 plus I times a real number. And we couple it to another Liouville CFT with central charge 13 minus I lambda. And we couple it to the BC ghosts with central charge minus 26 as usual. Now, this is a particularly nice setup, and more generally, you can consider the worldsheet theory whenever these two central charges add up to 26, as long as you're away from the half-lines where you have to instead consider a time like Liouville. Those correspond to the situations that was discussed this morning. Now, I actually don't have to give you this crash course on Liouville CFT. You're all experts because you heard Victor's talk. I just want to highlight one thing here. The first is that to reiterate that we'll be considering the situation where B has this pi over 4 phase, and it will be convenient in this theory to characterize the primaries in the spectrum with what we call little p, which is like I times capital P, and that's just to get rid of some i's that appear in various formulas. So as before, we know all the CFT data of the theory, and we can compute any local observable we wish from the conformal block expansion using these DOZZ formulas. And as this morning, we create on-shell vertex operators by pairing primaries in the two Liouville CFTs with P minus equals IP plus and B minus equals minus IB plus. And from now on, I'm going to omit the plus and minus labels on B and P because they'll always be paired in this way. Now, observables, string amplitudes, are computed as usual in string theory by integrating CFT correlation functions over the moduli space of the worldsheet. So these are the string amplitudes that we call AGN. They depend on the P or on the N external momenta, and they're computed by integrating the product of these two Liouville CFT correlators paired with the BC ghost as usual over the moduli space of the Riemann surface. Now, I kind of want to sweep this under the rug, but it turns out to be convenient in this theory to introduce some leg pull factors, some overall normalization of the external operators, but don't worry too much about this. Okay, so in the bulk of the talk, I'm going to focus on the particular choice, as I've said many times already, corresponding to central charge having real part 13. It will also be convenient, and I don't think I have said this yet, to consider the case where the Liouville momenta, little p, have the opposite phase, so e to the minus pi I over 4. And these correspond to conformal weights equal to a half plus I times the reals. And this will turn out to be a particularly convenient choice. For one thing, in this situation, the two Liouville CFT correlation functions are complex conjugates of each other. So the correlation functions of these on-shell vertex operators can be realized as an absolute value squared. And just as a comment I'll make in passing for now, these conformal weights, when paired with the left movers, correspond to the principal series representations of SL2C. So in this situation, when you pick these values for the central charge and conformal weights, the integral over the moduli space of Riemann surfaces is absolutely convergent, like it was in the earlier talk. And as I said earlier, the integrand turns out to be an absolute value square. Now, it'll be particularly interesting to consider the analytic continuation of the string amplitudes away from this locus, particularly in the Liouville momenta P, which will reveal a rich analytic structure of the full amplitude. So let's get right into it and discuss the simplest observable in the theory, the sphere 3-point amplitude. Okay, so as I said, this is the simplest thing you can compute in the theory because there's no integration over the moduli space to consider. And we'll see that this observable admits a number of different representations, each of which will make different various physical aspects manifest. So the sphere 3-point amplitude is up to the like pole factors simply given by the product of DOZZ formulas in the two Liouville theories. Now, in this morning's talk, this second DOZZ formula was a time-like DOZZ formula, and the two exactly canceled out. Here, that does not happen. So we have to leverage the fact that we know all there is to know about this DOZZ formula, which in particular is some meromorphic function of these momenta P1, P2, P3, with these infinite half lattices of poles formed by translations by multiples of B and B inverse. So when we combine with the other DOZZ formula, the full sphere 3-point amplitude has poles that arranged in this full lattice of points in the complex, say, P3 plane. But notice that this region, this line where P3 is e to the minus pi I over 4 times reals is always protected. It lies in between these wedges of poles. Now, somewhat remarkably, this combination of DOZZ formulas has actually was already studied by Zamolodchikov almost 20 years ago in a slightly different context. And what he showed was that, in fact, the full answer can be realized in terms of ordinary elliptic theta functions as follows. So this is the sphere 3-point amplitude. It depends on the three momenta, P1, P2, P3. And you have these theta functions, theta 1 that appear in this factorized way, and theta 3 that mix the three in the denominator. And it explicitly realizes these poles of the amplitude via the zeros of this theta function. I'm saying in the main case of interest in this talk, B squared is imaginary, but we can consider this formula in the more general situation that B squared lives in the upper half plane. Now, this amplitude exhibits the following symmetries viewed as transformations on B. The first two are just symmetries of the Liouville path integral, nothing fancy there. And the signs, by the way, that you pick up, those just come from the like pole factors, so don't worry too much about that. And there's this third one where you send B to minus IB and P to IP. And that corresponds to swapping the two Liouville theories. And when you combine all of these duality symmetries, you can in fact arrange it so that you take B to I over B. And this realizes the modular S transform on this B squared parameter, under which the transformation properties of the theta functions are, of course, well known. Now, curiously, if you identify the parameters in a suitable way, precisely this combination has appeared very recently in the literature as the boundary 2-point function in double-scaled SYK. I want to highlight in particular these papers by Vladi, Herman, and Mengyan from the past year or so. I won't have much more to say about this, but understanding the relation between their picture and ours is an interesting open question. Okay, here's another representation of the sphere 3-point amplitude that will turn out to be convenient and that will keep showing up as the talk progresses. The sphere 3-point amplitude can also be written in terms of the following infinite sum. So there's this integer m that we sum over from 1 to infinity, and there's a factor of sine 2 pi mbp for each of the three momenta, divided by this overall factor. Now, this obscures basically all of the nice properties that I told you about in the previous slides. And to convince yourself that it satisfies the properties we need it to, we note that it can be obtained from a contour integral of this quantity over the following contour. So this integrand has 4 rays of poles, basically at multiples of b over 2 and b inverse over 2. And if you take the contour to wrap one of the rays of poles, in particular this ray, then you reproduce this formula. And then you can use symmetry properties of the integrand to arrange it so that the contour wraps around any of the other rays of poles. So that in particular explains the b to 1 over b symmetry. Okay, so with that under our belt, let's move on and discuss a more complicated observable. Are there any questions about this before I move on? Okay, good. Now, to compute more general string amplitudes, we of course have to integrate Liouville CFT correlation functions over the moduli space of Riemann surfaces. And in general, this is complicated and tedious. However, with some hard work, it is at least possible to integrate numerically for some low values of g and n. Now, as I tried to emphasize at the beginning, on the other hand, we know basically all there is to know about the Liouville CFT. So we can leverage this exact solution via the DOZZ formula to reveal the analytic structure of the string amplitudes, which will give us with some essential clues about their exact forms. So let's look at the sphere 4-point amplitude in more detail. The building blocks are these sphere 4-point functions in Liouville CFT that admit a conformal block expansion. Some integral over DOZZ formulas weighted by the conformal blocks in a particular channel. So from this, we can infer the analytic structure of the full string amplitude. So for one thing, we notice that when poles of the DOZZ formula cross the contour of integration, which here I've taken to be this vertical line, then there are additional discrete contributions in addition to this continuum integral. So when, for example, one of these right-moving poles that I call P star crosses the contour so that real P star is less than 0, then we have to pick up the associated residue to the conformal block expansion. Now there can be poles in the full 4-point function when singularities of the DOZZ formulas pinch the contour of integration. And this happens when the 4 momenta saturate some background charge. And to anyone that's ever worked in the Coulomb gas formalism, this condition is probably familiar. Finally, there are discontinuities in the full string amplitude. And these occur when these discrete contributions coming from poles of DOZZ crossing the contour, they can cause the moduli integral to cease to diverge. And so if we look at the P star plane, there's this wedge of divergence with real P star less than 0 so that it's crossed the contour, and real P star squared bigger than 0 so that the moduli integral doesn't converge. And so you want to compute the string amplitude by analytic continuation from a region where it converges inside this wedge. And it turns out that the answer that you get depends on whether you continue from above or below in this wedge. And so what that means is that the full sphere 4-point amplitude, A04, exhibits a discontinuity around P star equals 0. And that discontinuity is actually proportional to the residue of the product of sphere 3-point amplitudes. I may have more to say about this at the end. Okay, so these wedges of divergence that are associated with these branch cuts carve out a domain of analyticity in, say, the pi plus pj plane for any pair of external momenta. And in the case that B has this special phase, this region is non-compact and includes our favorite 45-degree lines. But in the case that B does not have this 45-degree phase, then the region of analyticity that's carved out is in fact compact. Basically, these wedges eventually close on each other. Okay, so I've told you a lot of properties of the sphere 4-point amplitude, and it turns out that you can use these analytic properties together with the duality symmetry and some other properties that I don't have time to discuss in much detail to essentially bootstrap the full answer. And it turns out that a solution is given by the following somewhat complicated, but I promise manageable formula. So let's unpack it. There are 2 kinds of terms in this amplitude. There's the first that involves a double sum over M1 and M2, two positive integers. And what you notice is that the summand that you get here is exactly what you would get if you had integrated a product of two 3-point amplitudes in the appropriate channel with this measure, 2p dp. And here the prime on the integration just means that I arbitrarily throw out some divergent terms in this integral. That's related to the 1 minus delta M1, M2 in the numerator up here. Now, this term with the double sum actually generates the discontinuities of the sphere amplitude. If you further process it and actually evaluate these sums, you get some dilogarithms, which exhibit logarithmic discontinuities. Now, there's a second meromorphic term. This just involves a single sum with, again, these sine 2 pi mbp factors for each momentum. And quite interestingly, the coefficient here is precisely the quantum volume that Victor talked about earlier this morning, but analytically continued to the region of parameters of interest. And this was a priori quite unexpected. Now, this may look contrived or, or at least very complicated, but we're at least able to confirm this by direct numerical integration over the moduli space. So on the left here, we have the situation where we have B with the pi over 4 phase and the corresponding phase for the momenta as a function of one of the absolute values of one of the momenta. And we observe a match with error less than like 10 to the minus 5%. Yep.
Go back a second.
Yeah.
So this was a form that you guessed by matching with a certain analytic structure, or this was something that you got from more context?
The former, yeah.
And it happens to match this.
Yeah, there are other constraints I haven't told you about beyond these analytic properties that we can discuss after that was provided some input into this guess, but essentially, yes.
And when you say it depends on these zero minimal string quantum values,
yep.
How are the parameters of the zero minimal string that you use to compute that related to the parameters of your Liouville squared string?
You can view these as, so these were polynomials in the momenta and B, the central charge, right? And you simply evaluate them with the values of B and P corresponding to the situation of interest. Yeah, thanks for the question. Good, okay, yes, and on the right here we have, we consider the case where we don't give B this special phase and give kind of random phases to the external momenta, computed as a function of the absolute values of one of the momenta, and again, we observe a remarkable match. So we have a lot of confidence in this formula. Are there any more questions about the 4-point function before I move on? Okay. So let's give a first glimpse of this dual matrix model. So we saw in our discussion of the 4-point function that the full amplitude involved the analytic continuation of this VMS quantum volume. Analytically continued, I mean, to the range of parameters of interest. We also saw that at least the discontinuous part of the amplitude could be obtained from an integral of these lower point amplitudes, A03 times A03. So to my mind, both of these properties are sort of begging to be explained by some underlying structure. And indeed, we've acquired a significant amount of evidence that the most general string amplitude can be expressed in terms of what's known as a sum over colored stable graphs. So I have to tell you what essentially all of these words mean. So what is a stable graph? You can think of a stable graph. So first, consider some Riemann surface, say genus G with n punctures, and enumerate the different ways in which that Riemann surface can degenerate. Each of those is associated to what's known as a stable graph. And each stable graph is itself made up of a bunch of components, with each component being some Riemann surface of genus G with n punctures glued along what are known as nodal points, so like some internal lines. And colored just means that associated to each vertex, we associate an integer, a positive integer. And those are the m variables that appeared previously in for example, this slide. Good. And moreover, for each component or vertex of these stable graphs, we associate a factor of the VMS quantum volume. So let's unpack this formula a little bit. So for the general genus G endpoint amplitude, we sum over all stable graphs corresponding to degenerations of the Riemann surface. Now, like when doing Feynman diagrams in quantum field theory, we have to divide by the automorphism group of the stable graphs. Basically, those just come from interchanging various internal lines or nodal points along which you glue the components. Now, there's a factor like this for each vertex or component of the graph raised to the power of minus the Euler characteristic. And we integrate all of the nodal lines, all of the internal lines. We assign them a Liouville momentum and integrate them, say, from 0 to infinity or along the minus 45-degree line. Now, for each leg of the graph, we associate a sine 2 pi mbp factor, where m is the integer associated with the coloring of the vertex. And finally, as promised, there's a factor of the quantum volume for each component of the graph. And we've checked that this gives an answer at least compatible with all of the known symmetry constraints for genus 0 up to 5 point, genus 1 up to 3 point, and for genus 2, I think just the 0 point. So we have a fair amount of confidence in this formula. So just to make it a little bit more concrete, let's revisit the sphere 4-point amplitude that I wrote down earlier. I want to argue that the two terms can be interpreted as the two topologically distinct stable graphs. So the stable graphs, I should say, are labeled by this integer in the middle, which is the genus. So the first, which involved two sums, comes from gluing together these two sphere 3-point components or vertices. And there's an integral over the momentum associated to this internal line, weighted by the quantum volumes of the 3-point function. But of course, as Victor told you this morning, those are just one. And then you sum over the various permutations of the external legs. The final term, which involved just a single sum, you could associate to the sphere 4-point vertex itself. So here there are no internal lines, so there's no gluing or integration to be done. You just pick up a factor of sine 2 pi mbp for each external leg and a factor of the Virasoro minimal string quantum volume. So the structure seems to be that in this sum over stable graphs, we can interpret the VMS quantum volumes as a sort of string vertex. And just to make it even more concrete, here's a cartoon of all of the stable graphs you can write down for the torus 2-point function. So in this situation, there are 5. Some of them come with a factor of 1/2, which is just the symmetry factor I mentioned earlier. And, so there's the torus 2-point vertex itself. There's one that you get by gluing the sphere 4-point vertex to itself, and so on and so forth. And so you can play this game for whichever string amplitude you wish. And I mention this because the structure of this involving this sum over stable graphs turns out to be exactly like that which appears in topological recursion. And what this indicates to us is the existence of a dual two-matrix integral, which is characterized by the following spectral curve, which has infinitely many branch points. So here we have x of z is cosine of 1 over b times z, and y of z is just cosine of b times z. And for the experts, or perhaps even people with historical literacy in the literature, this is remarkably similar to the ordinary p comma q minimal string. It's essentially just in the situation in the minimal string, b squared instead was a negative rational number. And from this spectral curve, we can compute the initial data for the topological recursion. So first is this leading differential, omega 0, 1. In the Virasoro minimal string, the only difference was that this cosine was a sine. And omega 0, 2 takes the canonical form in matrix integrals, but dressed with this correction term, and turns out to be important. You can change variables slightly so that omega 0, 2 takes the standard form, but we like these z variables. Now, what the topological recursion does for you is it computes arbitrary differentials omega gn, based just entirely on this input, omega 01 and omega 02. And what we've found is that these string amplitudes are simply related to these differentials, omega gn, by inverse Laplace transform. So we compute these via, say, topological recursion, and compute the inverse Laplace transform with this funny contour I showed you earlier. And this can be realized as a sum over the branch points. So you can view these sum over integers m1 through mn as the sum over branch points associated with this spectral curve. And these were the colorings in the sum over stable graphs. So you sum over these residues of this combination, and you can compute the string amplitude. And we've checked this for a number of examples. So then what you can do is translate the topological recursion for the differentials omega directly into a recursion relation for the string amplitudes themselves. This is some generalization, if you wish, of Mirzakhani's recursion relation for the Weil-Petersen volumes. Now, some of the details of that formula, such that I trust the various coefficients that appear, are still work in progress, but there is a formula. Okay, so I'm basically out of time, so let me just conclude with some loose ends and things we're thinking about. The first is to better flesh out this worldsheet sign dilaton gravity picture and the relation with ADS and DS2 vacua. And in particular, it would be interesting to study better the semi-classical limit of these string diagrams and understand their relation to dilaton gravity. In the Virasoro minimal string, the semi-classical limit of the quantum volumes was just the Weil-Petersen volume. So you could ask, what happens in this theory when you take the imaginary part of the central charge to infinity? I think there's an interesting target space picture for this theory. We don't understand it very well, and it's likely to be conceptually quite different from the Virasoro minimal string. In particular, I think there's hope that you can interpret the discontinuities of the amplitudes as expressing perturbative unitarity in some target space theory. So we factorize the theory on some set of on-shell states. Now, the matrix model itself also deserves to be better understood. We want to recast the topological recursion as the loop equations for this two-matrix integral. There's the sum over genera and non-perturbative effects in the theory that are presumably associated with ZZ instantons in this specific worldsheet theory. And finally, and perhaps most intriguingly, there's the question of the 3D interpretation. Now, in this Virasoro minimal string, in some sense, the key to deriving the duality between the string theory on the one hand and the matrix integral on the other was an elegant relation with 3D gravity or Virasoro TQFT on sigma times S1. And it's fair to question whether there's an analogous structure here, although, of course, it will differ quite significantly in the details. And just one small point in favor of that is that there appears to be an underlying SL2C structure in the worldsheet theory. So I mentioned the principal series representations earlier. You can also rearrange the Mobius generators of the two Virasoro algebras, and they combine into an SL2C algebra. It enhances the SL2R to an SL2C, if you wish, when you combine the two theories with the appropriate reality conditions. There's an intersection theory interpretation of the string amplitudes. After all, they involve the VMS quantum volumes, and that begs to be better understood. And as I already mentioned, we'd like to better understand the relation to this work by Vladi, Herman, and Meng Yang. So with that, I'll conclude and say thanks for your time.
So am I understanding correctly that your resulting amplitude can be uncontinued to the complex center charge plane away from the cuts?
Yeah.
And what happens if you take the limits where the center goes to 1 and 25 respectively?
Good question. We don't know. We haven't investigated it. You're anticipating some relation with C equals 1?
Well, it would not exactly C equals 1,
yeah,
because
right.
the free bond have to be replaced by the Runkel-Watts theory.
Exactly, yeah. But the answer is we haven't looked into it very carefully.
So this SL2C, you can think of as a Möbius symmetry, so this suggests some dual 2D CFT description, or?
Not a conventional one, but yeah, something like that. I mean, SL2C, of course, we think of as the isometry group of Lorentzian DS3. But, you know, I'll leave it at that.
And also, so your momenta always lie just along these 45-degree lines, or is your worldsheet theory involving?
A priori, they live on this 45-degree line, but it's fruitful to consider the analytic continuation away from there, because that's, after all, how we learn about these, you know, poles and discontinuities.
But if you were to take them, would that be the modular invariant worldsheet theory, or have you thought about whether that's by itself a consistency
you mean
worldsheet?
if I think of the internal spectrum in terms of the states on this 45-degree line? Yeah, I kind of glossed over that. Yeah, we think so. In this case, the P integrals are all kind of marginally convergent because they're just phases asymptotically. We think so, but it still remains to be understood. Yeah. I mean, one comment I'll make is that if you start with this vertical contour in the, say, conformal block expansion of the 4-point function, if the momenta satisfy the property I've said a number of times, they live on this 45-degree line, then it's safe to consider you can rotate the contour and no poles cross it.
Could you remind us the dilaton gravity, what is the difference between the dilaton gravity theory you get here and the case of the time-like and space-like?
It's a sine versus sinh.
But so what is the contour? You integrate the capital
That
phi?
is a very good question that I do not understand very well, to be honest. A priori, if you follow your nose from the field redefinitions of the Liouville CFT, then it's a real contour, which of course is very different from JT, for example.
But also, isn't it, the action is periodic in
Yeah.
phi, so the real contour doesn't sound, maybe a periodic real
Maybe
contour?
periodic, but we have not understood it very carefully from the level of the dilaton gravity theory.
So if I understand correctly, the target space interpretation would contain an asymptotic region where you have an R2, two directions, one time-like, one space-like?
Presumably.
I see. So can you view this as a particular background of the =1 background? Or?
That's a very good question. I don't know, but it would be very interesting if so. Yeah, we don't know.
I have a much more elementary question, which I just missed in the beginning.
Sure.
In the semi-classical picture, are the de Sitters perturbatively stable?
Good question. We also don't understand that, whether they're stable or not. The expectation would be that they're not, but from this analysis, it's not obvious because they correspond to zeros rather than extrema of the potential. But you'd have to study fluctuations around those backgrounds, and that's just an analysis we haven't carried out yet.
Other questions? Anyone on Zoom? All right, if not, let's thank the speaker again.